Today, let's talk about the nighttime car detection. Vehicle detection has been applied in many areas, like driver assistance system, self-driving car, traffic control. Vision-based on-road vehicle detection we are going to talk about today is that the camera is mounted on the vehicle and the viewpoint is not changed. Basically, the viewpoint is the viewpoint of the drivers. It's the monocular vision. It is the 2D vision, not the 3D vision. And nighttime vehicle detection is very challenging since it is confronted with the great variance of illumination conditions, and many algorithms of daytime is probably not applicable. The trends and challenges of car detection. Our ultimate goal is self-driving, and vehicle detection is an important part of that, and it has been started years ago. And the sensors we use for vehicle detection are mainly in two parts, two main kinds. One is active sensors like radar and laser, and passive sensors like optical sensors, many kinds of cameras. Vision-based car detection basically has two parts, hypothesis generation and hypothesis verification. Some early research is LOC plus neural network, and later we use color and symmetry, HOG plus FSVM, MDPM plus FSVM, CNN based, and some features like shadows, edges are used. Let's talk about the outline of the studies. First of all, we'll talk about the hypothesis generation, then hypothesis verification, and last we'll make a conclusion. To evaluate those research, we use criteria that if the algorithm can be used at nighttime. Since the illumination is a great challenge, we'll see if the algorithm can handle the great variance of illumination and if the algorithm can succeed instead of the dim outside of the arrows. First of all, let's talk about the hypothesis generation. Some early sorts process the images and then use histogram features to present each block of the feature of the images. The equation like this is used to transform the image, and in matrix form it is like this, and we compute the histogram features for each row and each column and use these two features to represent each block of the image. Some other early source is to use the image processing, and then you binarize the image by predefined threshold, and we get image like this. To fill the holes of each area, we need some graphic methods. These early results are too simple and can be fit for the variation of illumination. The predefined threshold prevents them from having better performance. Some other features are used, like shadows. It is probably applicable for daytime but not for nighttime. The largest variance threshold segmentation is used to binarize the image and use the image erosion to transform the shadow arrow into a well-defined arrow and use that as a candidate of the cars. HOG is a widely used method for car detection. Basically, the method should scan the whole image by windows and generalize the HOG features for each windows. For each windows, a gradient image is get by the matrix, and we use the variable size of overlapping blocks to get the histogram feature of the image and use that feature for our later computation. Also, AR-like features plus add the boost is used to generalize the candidate for cars. The AR-like feature is used to generalize the gray level distribution of 2 or 3 adjacent regions and use that information to get the horizontal and vertical edges of the cars. After that, we get a bunch of car arrows, and we use the add-boost method to remove those arrows are probably not the vehicle arrows and get a smaller set of vehicle arrows. Recently, MDPM is used. It is a model that presents the car using the deformable part. M is the model for the car, and MC prevents a deformable part of the model. This is represent method, and for each MC we use HOG features. For nighttime car detection, red light detection is very promising method. It segments the red lines from the car and transform the image into PAL RGB color space, and then transform RGB to HSV, and using the HSV threshold to binaryze the image and get the lamp arrows of the image and use that for the candidate of the cars. Then let's talk about the hypothesis verification. Neural networks we use after we get the features of each blocks of the image. We use that as the input and train the neural network, and after that we use this as the classifier to classify the candidates of unlabeled images and see if they are cars or not. SVM is the broadly used classifier, and it is very hot and general these years. And symmetry is also used for the car detection, since the car is almost symmetric in the images. Light candidate pairing is a good example. After getting the light arrows of the images, we will use compute the parameter gamma to see the cross correlation of the images, and threshold is used to see if the two pairs of the lamp is belonging to the same cars or not. Latest studies have been using CNN to extract the features from the image. For each layer, a matrix used to transform the image into another image. And after several layers, we get a vector-like feature of the image. And then we use SVM to classify those features and see if the image contains cars or not. In conclusion, for HG, shadow and edge-based methods are not promising at night. There are no shadows and obvious edges at night. Edge-based method like MDPM can be expensive since it scans all the images. It is unknown if it can be applied for nighttime detection. Car-based method can be applied as a part of the method since it puts great value on the lamp of the cars, and the lamp of cars are really obvious at night. But we have to see if it can resist the noises. For hypothesis verification, SVM is a general method, and CNN can be tried, but the database should be large and the computational assumptions heavy. This is our references. Thanks for watching.